Hello, welcome to a new lecture. So in the last lecture we talked about the intuition behind transformers and how we kind of take this hidden state, we project it to QKV. We had this really great buffet analogy. And today we're going to ground a lot of our understanding in code. So down here I have just some like common transformer code. And we'll just quickly walk through it. So last time we talked about how we project the hidden state into QKV. In practice, when you look at transformer code, you oftentimes see this, like hidden mapmode weight of QKV. But it's important to note that this is morally equivalent to doing it separately, where you say like Q is a hidden mapmole with the weight of Q, similar with K and V. It's just that this kind of fuses it into a single kernel and it's more efficient. And after you calculate QKV, you need to kind of re-split it out. So you split out this QKV intermediate tensor back into QKV. And then oftentimes in transformers, you actually see this reshape. And this reshape has this like term in the middle, which is called heads. And the basic intuition behind heads is that it might like it's sometimes useful to have different like diversity of perspectives. So like going back to this like buffet example, it might be the equivalent of like if you're like trying to get food for the table and you have like one vegetarian and like one carnivore and like one pescatarian or something. Then like they'll have different queries, like they're literally different heads of people. And so it's useful to kind of have these like different perspectives. And so we basically have this additional dimension for head when we do the attention. It's also important to call out that in practice, like especially we're going to talk about preflow decode in the future, but in practice, when we're doing prediction, at least decode, this is actually just a batch size of one dimension tensor, caveated with, we'll batch with other requests, but, for a particular user, it's going to be size 1. And this is where the KV cache comes into play, where, we're going to have the size 1 tensor. We're going to calculate Q, K, and V for this one token. And then what we're going to do is we're going to write the K, and the V associated with this particular token into the KV cache. And then what we're going to do is we're going to do a mapmole of our query, which again is a single token, with the cached K. And this cached K, you can morally think about it as our K appended onto all of the past tokens we've generated. And again, so this gives us the attention matrix. And then down here, we multiply it with the cached V. And the cached V is our V appended with all of the past Vs that we've generated. And so you can see here like the magic of the KV cache, where we're memoizing all of this intermediate computation. And then the other thing I'll call out is that this happens per transformer layer. It's not like you have one KV cache for the entire model. Per transformer layer, you have these KV caches. So just high level, I want to build that intuition that we're doing this memoization, and we can leverage the fact that as we're generating more tokens, the K and the V don't change for the past tokens. And that's why we can do this memoization. Okay, so after you do the attention, you'll notice that we do effectively like an MLP. So first we do the RMSNorm. So what is RMSNorm? You'll see this oftentimes in code. It's basically this math, but I'm not going to go into the math, I'm going to go into the intuition. The basic idea is that when you're doing these attention computations, you're kind of like moving around points on like a very high dimensional plane. And hand wave, for training reasons, it's useful to normalize the values in this range. And so in practice, when you do something like RMSNorm, you're kind of like taking all these points and bringing them together into this sphere. And so across these layers, the values keep getting normalized, and that's what helps training. You can see more in this video, which I got the screenshot from. But I just want to call out because you'll see RMSNorm all the time. And this is the basic intuition behind what it's doing. Okay, so after you do the RMSNorm, you're going to do this gated MLP projection. And what this means is the following. So basic intuition is, in the same way that you kind of have QK giving you an attention score, which you then multiply by V to kind of weight V according to it. You have this gated MLP projection where you take the output of your attention and then you project it to two separate intermediate tensors, a gate and then an up. And the intuition is the up is your features, it's kind of like V, and then gate is going to be the relative weighting of the features. And so you have 512, you project it up to 1024 or whatever your gate dimension is. You apply this thing called SILU, which is an activation function, and then you get this intermediate tensor that represents the weighting. And then down here, you project up 512 to 1024 for this up tensor, which represents your features. Then you interact these two tensors together, and then you down project. Again, I'm not going to go into the theory behind why you want to do this, but this is very common in transformers where you do attention and MLP. So this kind of covers the high-level basics of what's going on within a transformer. And then in the next few lectures, we're going to go through some like very common inference techniques for optimization. Okay, see you in the next one.